Welcome to the Explainer. Today we're going to crack a classic coding challenge, one that's a huge favorite in technical interviews. It might look a little intimidating at first, but stick with me because underneath it all is a really beautiful and simple solution.
Okay, so here's how we're going to tackle this. First, we'll break down what the challenge is actually asking for. Then, we'll uncover the secret first step that unlocks everything. After that, we'll get into the main event, a technique I call the two-pointer squeeze. We'll see the aha moment that makes it so powerful, put the whole algorithm together, and finally, talk about why this is a bigger deal than just this one problem.
All right, first things first. What exactly is the mission here? Let's get a crystal clear picture of the puzzle we need to solve.
So here's the deal. We get a list of numbers, an array, and some target value. Our job is to figure out exactly how many different combinations of three numbers from that list add up to something less than our target. Okay, let's make this real with an example. Say our numbers are -2, 0, 1, 3, and the target is 2. We need to find groups of 3 that sum up to less than 2. Let's see. How about -2, 0, and 1? Add them up, you get -1. Yep, that's less than 2, so that's 1. What about -2, 0, and 3? That gives us a sum of 1. Still less than 2. That's our second one. And I think that's all of them. So our final answer here, it's 2. Now you could just, try every single possible combination of 3. But trust me, for a big list, that would take forever. There's a much, much smarter way to do this. And it all hinges on one simple action right at the beginning. And that simple action is sorting the array. I know, it sounds almost too easy, but this is the key. When the numbers are all jumbled up, we know nothing. But once we put them in order, from smallest to largest, we can suddenly make all sorts of powerful assumptions. That order is everything. Okay, now that our array is nice and sorted, we can bring in the master technique. This is the real heart of the solution, a strategy I like to call the two-pointer squeeze. So here's the plan. We're going to loop through the array, and on each pass, we'll just fix one number in place. That's going to be the first number of our potential triplet. Then instead of searching randomly, we'll use two other pointers to zero in on the other two numbers. Let's see it in action with our sorted array, which is -2, 0, 1, 3. We'll start by locking our first pointer, I, on the very first number, -2. Then we bring in our other two players, a left pointer, j, which starts at the next number, 0, and a right pointer, k, which we park at the very end of the array, on 3. Okay, time to check the sum. We've got our 3 pointers pointing at -2, 0, and 3. Add those together, and we get 1. Awesome. 1 is less than our target of 2. So we found a working combination. But hold on, this is the crucial moment. Finding this one triplet actually reveals something way more powerful. There's a hidden insight here. And this right here, this is the aha moment. This is the single idea that makes this whole algorithm so incredibly efficient. Right, think about this for a second. The array is sorted. That means the number at our k pointer, 3 in this case, is the biggest possible third number we could have picked to go with -2 and 0. So if even this largest combination works, well, it's a no-brainer that any smaller number we swap in for that 3 is also going to work, right? It's guaranteed. And that is massive. It means we don't just add 1 to our count, nope. We can instantly count all the valid triplets that we can make with -2 and 0. And how many is that? It's simply the distance between our two pointers, k and j. So in our example, k is at index 3, j is at index 1, so k minus j is 2. And just like that, bam, we've found two valid triplets in a single check, -2, 0, 3, and -2, 0, 1. Now that we've exhausted the possibilities with 0, we can confidently slide our j pointer over to the right and try again with the next number. And what if the sum was too big? Well, the logic is just as elegant. Since the array is sorted, all we have to do is move our right pointer, k, one step to the left. That brings in a smaller number, which guarantees our next sum will be smaller. It's beautiful. Okay, let's zoom out and put all these pieces together. What does the complete blueprint for solving this look like? It's really just a 4-step dance. Step 1. Sort the array, non-negotiable. Step 2, start a loop with your main I pointer. Step 3, for every I, you set up your j pointer just after it and your k pointer at the very end, and step 4, you just squeeze them. If the sum's good, count your wins by adding k minus j, then move j forward. If the sum's too big, just move k back.
That's the whole thing?
And here's the payoff. The brute force way, checking everything, that's what we call O of n cubed. It gets slow, really slow. But our smart method, with sorting and 2 pointers, that's ANO squared. Now, that might not sound like a huge difference, but believe me, when you're dealing with thousands or millions of items, it's the difference between a solution that works and one that just times out.
So let's wrap this up. Why did we go so deep on this one problem? What's the big takeaway here?
Look, the real prize here isn't just the answer to 3 sums smaller. It's the pattern. This idea of sorting an array and then using 2 pointers to squeeze in on an answer, that is a powerhouse tool you can add to your problem-solving toolkit. It turns messy, slow problems into clean, fast solutions. So, the real question I want to leave you with is this. Now that you know this technique, what other problems that seemed impossible